Okay, yeah, thank you for the introduction. It's my great pleasure to give this presentation. Okay, so this presentation is about microprocessor design. So I started with one example that many people are somewhat familiar with. That is the microprocessors in iPhones. So if you look at from left to right, we can see the microprocessor design progress from iPhone 8 to iPhone 13. And in iPhone 8, that is a 10 nanometer technology. It has 4.3 billion transistors. And now currently for iPhone 13, it is Apple A15 5 nanometer technology. It has 15 billion transistors. So we see this continuous progress of microprocessor technology. But these are the progress. And actually, it's not easy to get this progress because microprocessor design has its own challenges. One main design issue actually is power. And we all know the importance of power issue for portable or mobile electronics that is affect the battery life. And for even others cases, so the chart on the right, it is a little bit old, but it still shows something. That is to show that over the year, if we continue to crank up the performance without doing anything else, the power density will go to in an uncontrolled manner. It may go to like in a rocket also or nuclear reactor. Of course, we never been there because we have done something to cap it off, right? Okay, so this is one statistics on the designs of microprocessors. First, let's look at this diagonal region. That is the growth of number of transistors. Be careful, the vertical axis is in exponential, so that we have exponential growth of number of transistors over the years, right? But if we look at clock frequency, we pretty much stop increasing it about 20 years ago. And the one reason actually is this power limit. Because of power limit, you cannot crank up the frequency anymore. And from about 20 years ago, the strategy was to have a multi-core design. So by having this multi-core, we can control the power not explode. But on the other hand side, we see the progress of the performance growth is also slowed down. So so that power and performance are two constant issues or challenges that are faced by the microprocessor design. And another issue is we call it design productivity crisis. That is because of when the processor complexity grows, it takes more manpower and more time and more effort to design the microprocessor design. So you can see this is in terms of dollar amount, how much cost to design a microprocessor. Then how to address to these issues. So this is what this presentation about. Okay, and we're going to talk about power modeling because for microprocessor, power is important. We're going to talk about performance issue. These two are, I'll say, two most important issues for microprocessor design. And also because of the design productivity issue, we proposed to leverage machine learning techniques to solve this design productivity crisis issue. Okay, so let's first look at the power. Okay, so in this chart, you see if we increase the frequency, the power will goes up, and if we increase the number of cores, the power will goes up. So whenever you want to improve the performance, there are always price you paid on the power, but there's a fundamental limit on the chip power. And so in the middle of the chip design, you cannot just say we increase the power arbitrarily. We need to keep track. In the design time, we need to make sure the power does not blow up. So how to do that? And one approach is design time simulation. So we have some applications. We need to simulate them in the waveform. And we needed to have a design time power model. So by taking these trace of signals, we can have some estimate, hey, the power is good or bad, and then we can provide good design feedback. But this traditional power modeling methodology has its challenges is that this is simulation or some process is very, very slow. For the industry design, sometimes it may take weeks to do this simulation. It's really time consuming. And besides this design time power tracing, we also needed to monitor the power consumption at the runtime. And there are some previous techniques to do that, but typically they will cause large area overhead to do this monitoring. And you may ask, we have design time modeling, why do we need to also to do like runtime? First of all, design time is not always accurate. Okay, so runtime might be more accurate. And also in the runtime, besides the power dissipation itself, the power switches also will affect the power supply, the VDD and the ground. Okay, so you see this red curve. If there's a lot of switchings, the VDD level will have oscillation. By monitoring the power, you can trace down this power noise, which needed to be controlled in the chip operation as well. Okay, and because of the importance of this power modeling, people have studied for 15 or 20 years. Okay, and so this chart shows the trade-off for the power modeling. Okay, so there are 3 different levels of power models. One is architecture model. Architecture model is very brief. The good point is that you can simulate in architecture level very fast, but the accuracy is low. And gradually you can move down to more detail, register transfer level or gate level. And these simulations will provide much higher accuracy, but the problem is the simulation time is pretty long, too long. So there's a trade-off. Okay, so for example, for ARM Neuverse N1 processor, we spend like 1 hour just only simulate 20 cycle power traces. So it takes a long time, and also the data is huge. If we use FPGA emulation, it needed to handle huge data. For runtime monitor, either it costs over 10% chip area, or it has a cost resolution. It measures every 100 cycles, not per cycle. And what we propose is this work we call Apollo. And what we achieve actually is accuracy, somewhere between the RTL and the gate level. So it's very accurate, but the simulation time is much smaller. It is. So this is our work. Okay, Apollo. Okay, so now let's go to this the general framework of this power model. Okay, so we trace the power for each clock cycle. So this I here is the index of which clock cycle. So we look at time series. And so this is the P means the power of the chip power of 1 clock cycle. And the idea is that we extract some features, access feature, or we call the proxy signals. And we use some models to estimate the power based on this monitored signal. And typically, this signal people use register because register they have correlation of the signal switching. They are pretty representative of the switching activities. And one issue is that how to choose this function form. There are different approaches. You can have linear regression, or recently people use graph neural network. Graph neural network or neural network is very powerful, but the problem is that you cannot do that for on-chip monitor. That means you needed to implement a hardware neural network to monitor power. That is way too expensive. Actually, what we propose is just use a linear regression. Linear regression is simple. You may ask whether or not it's good enough. I will show whether or not it's good enough. Okay. So here is that this is on the left figure are the switchings of those registers, right? So if we look at A, register A, it has a switching here, and no switching here, no switching here. So we have a 1, 0, 0. So for for A, it says 1, 0, 0. Okay, so for register A, in clock cycle 0, there's 1 switching, no switching, and no switching. Okay, so for these register activities. We can extract them into vectors. And using register signal to monitor the power behavior is a common approach. But the problem is that in modern processor designs, the number of registers actually is pretty high. So for this one, for ARM Universe N1, it has 500,000, more than 500,000 registers. For Cortex A777, it has more than 1 million. So you have so many signals to monitor, and even have a linear regression. The computation actually it is expensive. So this is the original form. This is the raw features, and then this is the function. Then we can estimate the power. What is the power at clock 0, clock 1, and clock 2? Right. Okay. And so if we don't do anything, these are we call the raw signal. The raw signal means those raw register signal, and this is the linear expression, pretty simple. W prime is the weight for each linear signal, right? But the problem is that M is too huge, okay? So what we're going to do, actually, one key part is that we're going to do some pruning. We call it proxy selection. So that is for these registers, we prune out the most of them. We only keep a small set. We only keep a Q of them. So this Q is much smaller than the original M. And then we build a new model based on this selected Q. There are some previous approaches based on that one, but they use a clustering, and our result actually is better. This page, the idea actually is not hard, but it is pretty effective. The key idea is in this page. Okay, so the original model is that we have this raw signal, right? These are the signal switchings for one clock cycle. This is when we take a weighted sum, right? And what we do is that we do the pruning along with the training of this model. Okay, so this is a linear regression model, right? For linear regression model, so how to get this weighting factor, you can do training, similar as neural network training. So you can have labeled data. You can always have a simulation to train it, right? Okay. And so after the training, you can get this weighting factor. And the key part actually is the loss function in the training. The first part is the same as the original training. So yi is the label, p prime I is the estimator from this model. So you can tell this is so L2 norm error we're trying to minimize, right? So okay. Another key part is that along this training, we try to penalize the weighting factors itself. So that means over the iterations, we push all the weighting factor down. Okay. So there are two parts. We train the model at the same time. We try to reduce the value of those weighting factors. And because this reduction of these weighting factors, they're done at the same time of the training. And so the reduction rate of this W varies. It depends on different register. If a register is important, so this W prime will stay being a large value for a long time. And if it is not that important, it can, quickly we can suppress down because of this training part. Okay. And so another important part is that this penalty function, this penalty function is not the linear function. So this is the original linear function. So if there's an error, you just this is proportional to the error, right? And here this error is this is weight function. So what we do actually is called this minimax concave penalty. So you see, this is what we so this penalty function is like this green curve of this red curve. Okay, so the difference is that when a weight is small, the penalty rate actually is the same as the red one. But when the weight is large, actually we have less penalty. So that means if a weight is large, we know it is important. We want to keep them. We don't want to suppress them down. Only when the weight is small means they're not important in this model, and then we give a heavy, weight to press them down, So this is the key part. Okay, so I would say the key idea of this approach is pretty much this middle part. Okay, and after that, we can, so after a certain number of iterations, the majority of W prime becomes 0 because we penalize them. We try to minimize this loss function. So then we only keep a very teeny tiny small portion of non-zero one. And for this teeny tiny one, we started to retraining from scratch to get the new weighting factor. Then it's done. Okay. So this idea actually it's not hard. And so later on I will show you that the result is pretty good. And this work received the Micro Best Paper Award. And I think that there are several reasons. One is that the result is pretty good. And also it is simple. And actually this is developed when a student did internship in ARM. So ARM is already adopting this. Industry, they like to have simple solution, that they like that a lot, okay. And because this technique was developed when student did internship in ARM, these are validated in the 2 industry design, and one that is applied for AWS, and 77 used in for Qualcomm designs, okay. And so first I will show you how much register signal finally we keep. Okay, so for N1, we said originally there are 500,000 flip-flops. After we do the pruning, we keep only 160, teeny tiny. So that is about less than 0.03 total signal. And even so, even we still do this linear regression, the result actually is not bad. So we look at, this is the power traces, this red one is from RTL simulation, and this one, the green one, is from Apollo. They're not exactly the same, but given that such a huge, tremendous pruning, actually it is still pretty good. This is the mean square error, and this is the correlation. Okay. Originally, when they try to emulate do the emulation of the original data using all the register signal, they need to spend 2 weeks. But because of this huge pruning, actually, we can do the emulation only in a few minutes. So this is a huge improve. Okay. This page shows the comparison with some other works. Lasso is just same as our technique, but we use this linear penalty. Okay. PCA is principal component analysis. This is it's similar as clustering, try to do the pruning. And Apollo is ours. These 2 are 2 previous work. Simani was published in Micro a few years ago. They use a quadratic model. We use a linear. They use a quadratic model. So you see, it's not necessary that if the model is sophisticated, you get a better result. Not necessarily true. Okay, and this one, Primal was published in DAC. It is CNN model. Okay, so these are the result on 2 design. The left one is on N1. The right one is on A77. And vertical axis are the error, and the horizontal axis is the number of register we keep. Okay, so so this is what for Apollo, this is what we propose. So this is about 160, but we vary the number of register we keep. We can see if you increase the number of registers, you can reduce the error. The same trend you can see for A77, and so this one is better than Lasso. That is the linear penalty. It is also better than Simani, which is this quadratic model. These both Simani and Lasso, they do some pruning. And the other, sorry, this is PCI, I was wrong, it's not. Okay, so here we use a horizontal line because for Primal and the PCA, and it's not pruning, so they use the original number of registers. Okay, so Primal, you see its error is also pretty low, but the number of signals it uses is much more than what we use, 2 orders of magnitude more. Okay. And so this is for the design time modeling. And also this another advantage of this technique is because it's so simple, so compact. It is pretty good for on-chip runtime monitoring. Okay, so this is the model, right? This is the model, and you see there's one multiplication, right? And so if this one is this is a vector, we need to do multiplication, or like a Simani, they use a quadratic model, can be more complex. But the issue here is just that our signal, they're just switching signals. So they're binary. So if it is a binary, and actually we can do this computing without any multiplier, which is a switching on and off, So we can, so if this is 0, which is a shield out, this weighting factor, only 1, it is the 1, we take them in. So then our monitor, we don't need to have multiplier. If no multiplier, then the cost is it is pretty low. And the implementation is right in C code, and then we do high-level synthesis to generate RTL design, okay? And so for N1 processor, and if we use 159 this signals, and also for the weight, we also do bit width optimization. Okay, so this is the number of register signal we choose, and this is the number of bits, right? Number of bits, right? Okay, so and what we propose is somewhere here, and so if we use 160 register signal, if we choose the bit width to be 11, then the area overhead is less than 0.2%. The previous work, if they reach the same accuracy, they need to have about 10% area overhead. So this is very, very low overhead implementation. So this is another advantage of this work. This work can be applied both at design time and runtime. Okay. And so next, I'm going to move on the second part of this presentation. So this is about performance now, okay. And one trend we see that is the continuous growth of design complexity. When the complexity grows, then there's more chance of design bugs. When we write software, we're familiar with the debug. That's the same thing. Hardware, there's bugs as well. And actually, hardware debug is more complex than software, And we're considering one special kind of a bug we call a performance bug. And so what is a performance bug? Performance bug is that because of this bug, the functionality is not affected. The processors can still deliver the correct computation, but it has some unwanted performance loss. And be careful, we don't want to confuse this one with the design bottleneck. Design bottleneck is due to some resource constraint. But here the performance loss is due to design error, some mistake. There's some mistake. And performance bug exists in product, performance bug. In one previous example, in Xeon design, sometimes the performance, due to this bug, the performance loss can be over 10%, Then you may ask, like, hey, then how do you people handle that? Performance bug is something real, and industry people also they are dealing with that, but the way they deal with it is manual design. They just run simulation. They leverage designer's idea to see, something wrong, might be wrong. Let's just see what's going on, something like that. Okay. But if we look at the performance bug, it is very challenging, to solve, especially compared with a functional bug, because for functional bug you have a golden standard. Like a 3 plus 5 is equal to 8. If it is equal to 9, it's wrong, right? But for performance, it's different. Especially you have a new design. There's no golden reference. Even you make a mistake, you have some loss. It's not that obvious, And the reason is that if you have new design, the performance is different from the previous generation, it might be hidden. So this is one example. We look at Intel design of Ivy Bridge and Skylake, right? Okay, so the vertical axis, the performance, normalized performance. The blue ones are from Ivy Bridge, the red ones are from Skylake, and these are different benchmarks. We can see there's improvement, right? And so now if we introduce a bug for the Skylake, the new design, so the green one is bug-free, and red one, we introduce some bug. Sometimes, you know, the bug effect is not that big. Like, so in this case, only 2%. It is very hard to be caught by human eyes, okay? And now let's see, like, so what we're trying to do, we try to develop some automated technique to detect performance bugs, okay? And is there any previous work? There are very few, but one main approach is that they try to develop a golden model. They try to develop a reference model, okay? And that is fine, okay, but the problem is that the model itself is not necessarily, you know, accurate. And also it takes a long time to develop that model as well, okay? So what we're trying to do actually is, so what we're trying to do is that to develop a machine learning based approach. So for machine learning based approach, we can let the machine learning model to learn from the data to reduce the human design effort to address the design productivity, you know, crisis, and highly automate this process, okay? So we're trying to build like a machine learning techniques to automatically detect performance bugs. And here, this is some assumption. We needed to assume there are some previous bug-free legacy designs, as, you know, we can use them as training data, okay? And so this assumption in general is true because legacy design, they have been gone through those post-silicon debug. So I would say at least they don't have a large bugs. It's even like legacy design, they may still have a teeny tiny small bug, but typically they don't have large bugs. Okay, that is true. And later on we will show that even with there's a small bug, and from those legacy designs, our technique will still work. Okay, so this is this page shows the key idea. So for the power modeling, I show the single page, the most important one, right? And for this one, for the performance bug detection, this page shows you the key idea. Okay, this is data driven. Okay, and we first train a performance model. Okay, and this is key part, okay? So this performance model is trained with a bug-free design. This is important, trained by bug-free design. And assume we have legacy design, we can have those data to train this model, okay? And because this model is trained with this bug-free design, and if we apply it to a new bug-free design, it is supposed to work well because it's trained by bug-free design, okay? And we have a hypothesis is that, but if you apply this model trained from bug-free design, if you apply to, you know, to a buggy design, it won't work well. Because if a design has bug and no bug, they're different. And the model trained by bug-free design, they quite likely will fail for bug design. So this is the key part. And later on, it turned out to be true, okay? And so this model will not work well for bug design. So then we look at the errors for this model. So for a new design, if we see this model will still work well, pretty much likely, this new design does not have at least no big bug, you know. And if it fails, then there's something wrong. There's big, it turns out to be true. Okay. So this is the general. We first look at the performance model, and we still needed to have an architecture simulator, for example, Gen 5, and there's some program traces, and we need to simulate them. And so this machine learning model, this is a performance model, right? And what we predict actually is IPC, number of instructions per cycle. And for this model, what are the features we use? Actually, it's performance counters. And the reason we use performance counter, they're already there in many processor design. So we don't need to pay extra overhead. The performance counter already include a lot of useful information. Okay. But there are many counters, in the design, there could be hundreds of thousands of counters. And if we use all of them, and the model might be too complex, so we do some pruning to prune the counters to be like 20 or 40 for our performance model. So we keep, if a counter, has low correlation with IPC, we prune out. And if two counters, they're very similar, we prune out one of them. Okay. And so in our methodology, we use different application traces, multiple, not a single one. Not a single one will not work. We need to have multiple traces to make it work. So we use this concept of a probe. So what is a probe? And for each, so when we talk about this counter selection, for different trace, we have a different counter selection, because for different traces, different counters have different importances. So for one combination of a trace and its selected counters, we call a probe. Okay. So this is an overview. At the beginning, we train the model using bug-free design. And next, we use this model to, given a new design, we do the prediction. And then we look at the errors. Based on errors, we tell whether or not there's a bug in the new design. Okay. And because we use multiple traces, like n traces, so we have n different probe. And this is one program trace. This is not program trace. And this probe has its own selected counter, So we have a simulation, and this is our machine learning model. And then we do the comparison and then look at the error. And be careful, this is a time series, because this is the program trace is a time series, change over time. And this is this counter number and the predict IPC, they're also time series. Okay. Next is how to quantify the error. Okay. So on the left, we show that this is a time series. Horizontal axis is time, vertical axis is IPC, and the green one are from the architecture simulation, and the red one are from our model. There's some difference, right? So the lower figure plot the error. The error can be positive or negative, right? So we use this shaded area under the error curve as the error. So we have a trace, and then we look at this shaded area. We use this as the errors of this model prediction. We tried several. This one works the best. Okay. And in stage 2, first we take errors from stage 1, and then we build one classifier. This classifier takes the errors from the first stage, and then this classifier will tell whether or not this new design is a no bug or bug. So in general, the case is that if we see a large error, more likely there's bug. And if there's less error, then it's a small chance of bug. Okay. And for this classifier, actually, there's one challenge is that, and because our label, okay, so for each architecture, we can have multiple different traces. So we can have a lot of, and also the training data is for different time steps. We have a lot of training data, labeled data, right? But for the second stage classifier, we have very few training data. The reason is that we have only like one labeled data for one architecture, because the label is that the architecture has a bug or not, right? One architecture, we cannot have hundreds or thousands of architectures. Actually, we have only like about 20, architectures. Okay. So how to handle that case? So we built a customized classifier. It's not really a traditional model. So this is more, we look at the relative error with some normalization. but the normalization coefficient are trained by data. So this is customized. So this is so how to normalize them? We need to have error reference for every probe. A probe is one trace plus its counters, right? And we first have all the buggy data, and then we look at the mean of errors of the bug data, and it's the standard deviation. These are for all the architectures. For each architecture with, like with error, we put them. Okay, for this trace, we can have mean error. And also for like a bug-free error, we also generate a mean error and the standard deviation. And now so this is the raw error, right? All raw error from the original, from stage one. And the normalized error is this is one. So this is the gamma. So divided by this is mu of bug data plus this is the coefficient plus its standard deviation. This similarly for bug-free one. And so here are the rules. Okay, for like multiple traces, we look at the maximum among all the probes. The maximum among all the probes, if it is greater than a threshold, then we say there's a bug. Okay, there's a bug. And also we look at those compared with the bug-free designs, and if the average of them is greater than another threshold, we also classify as bug. And for all the other cases, we say it is bug-free. And so this is error, right? But we take a little bit of machine learning flavors that the coefficient, this alpha, and this eta, and this is lambda. These are all trained by data. It's not like we just specify some, right? And these are the experiment setup. We have 10 applications from spec, and we break them into SIM-point. SIM-point actually are short pieces. It's not whole trace. That is too long. We have a SIM-point, and each one has like 10 million instructions. And we also design some bug. Actually, design bug is not easy, because to verify our design bug. But our design bug is not from nowhere, and because we even for industry design, for Intel, they have errata. So we found their errata. We try to tweak those errata to get those bugs. So we created 14 main bug types. For each bug type, we have like 3 small variants. So totally there's like 42 types of bugs. And also later I'll show these bugs, we categorize them as small, medium, large according to their IPC impact. Some bug has a huge impact to IPC, some have a very small one. The simulation is Gen 5 out of order core with x86 ISA. And architectures, okay. So it's a little bit complex because we have 2 stages. And for the first stage, the performance, we need to use some architectures for the performance model training, okay. And then we needed to validate the model for the first stage. And then we use these to train the second stage classifier, and then the stage 2 testing. So these are the architectures. Totally, we have like 20 architectures, and 8 of them are based on real designs, like Intel and AMD designs. So we use this logo to represent real designs. And also we created like 12 artificial designs. This is necessary. This is necessary. Only real design, the data is not enough. Later on, I will show you that. So for some designs, we use some artificial. These designs really help, even though they're help. And first, we look at the first stage, the IPC prediction, error. So we compare lasso, linear regression, LSTM, CNN, MLP. This is a gradient boost tree. These are the training time and the inference error. That's a lot of data, but I will just highlight that actually the best one is gradient boost tree, or like a random for XG boost. its error is relatively low compared to others, and also the training time is also less, and also the inference time is also relative. This is a little bit long, several minutes, because we need to trace the time series. So this is why it takes such a long time. Okay, and so this is because of a time issue. I won't show too much. I need to skip it. Okay, so this is once to show you, like to illustrate, to verify our hypothesis. Okay, and so this is the time series of IPC for like one design. I forgot which one. The red one is from the architecture simulation. The blue one is from our machine learning model. You see, the machine learning model is well trained, so the difference is small. And but if we insert a bug, you see the error becomes large. Okay, so the model is trained with bug-free designs. Once you insert a bug, the model started to fail. Okay, and because of time, I won't spend too much of it. Because of this two-stage thing, the data set organization is a little bit complex. Some are using the first stage, second stage, some are bug-free, those kind of things. Okay, and previously I showed the accuracy of the first stage, the machine learning model. Next, we needed to show the bug detection. The bug detection, people may ask, hey, why do you need to have this two-stage thing? Why not you just have one machine learning model, give counter information and tell whether or not, give it output to see whether or not it works. Okay, so this we call a naive model. Just give those counter information and then try to directly tell, just one shot, give the raw information, tell, hey, this bug or not. You can, later on I will show that this result is not really good. So this is, in terms of results, I would say this is the most important page of the result. The first line is this single stage naive machine learning model, the baseline. We have just one stage, okay. And these are, the middle ones are our framework using different machine learning engines. Again, the best one is a gradient boost tree. And we look at the true positive and false positive, okay. So the best one actually is from the gradient boost tree. The true positive is about 80%, 84%, and with the 0 false alarm. And we also look at area and ROC curve. ROC curve is to look at the trade-off between true positive and the false positive, right? The overall trade-off, this one is gradient boost tree 250 is the best, get like a 0.9. And the perfect one is 1.0, 0.5 is random guess. So this is already pretty good. And this is a precision one. And here, this part is also important. We categorize those bugs according to their IPC impact. And I forgot the exact number. So this one high maybe above 10%, performance loss. I don't know, 5 or 1 or below. So more one. Okay, so it's not surprising that our technique works better for those medium and large bugs, and less good to detect those small bugs. But in reality, actually, I will argue that people care more about the large bugs. Yeah. If the bug is too small, people really don't care. Okay, so if the bug is large, like 5% or so, we have a large chance to capture them. Okay, and earlier I mentioned that we have an assumption that the original model for the performance model, we need to use a bug-free design, right? And people are, what if there's a still bug there? Because you cannot guarantee there's no bug, right? So we put some small bugs in the first stage model in the training. Okay, that causes some degradation, but still it's pretty good. So that means our method, still works, even though the original training data for the first stage, has some due to the time limiting, I'll just go fast for the other result. And here to show that if the impact of a number of probes or number of sim point we use, and so different methodology. In general, it will, when we reduce the number of probes, the false positive will go up. Okay, so it is necessary to have plenty of traces to train our data. And this is one to show the impact of counter selection. And this is ours. We have a true positive and a zero false positive. And if you use other method, you have a lot of false positive. And this one shows the impact of architecture samples. We created our artificial one. This is important, okay? And so if we remove those artificial one, we will have a lot of false positive. And also this is a time series, right? And our time step actually is a coarse grained. It is like a one clock cycle per time step, okay, time step. And so there's some sweet spot in this region. There's somewhere in the middle. Next, we also did some experiment for memory system. So for memory system, it is very similar, but we also, beside IPC, we also look at AMAT, average memory access time, and we get a similar result, a very high true positive and zero false positive. Here are some conclusions. And so we see the progress of microprocessor design technology, and we continuously need to solve this power issue, performance issue, and design productivity crisis. And we propose machine learning to help them. And for the power part, and we propose a modeling technique that can reduce design time, emulation time from 2 weeks to 2 minutes, and the overhead for on-chip monitor from 10% to 0.2%. And for performance bug detection, it mostly by manual. Now we propose a machine learning-based automatic approach. And these are the students who did this work and my collaborators and industry collaboration. I think that's all for my presentation. Yeah, thank you.